Welcome to the CFE Media and Technology session, How to Select Transfer Switches. I'm your moderator, Amara Razgis with CFE Media and Technology. In keeping with our CEP policy, please take some time to read this quality assurance slide. This session is designed for technicians and engineers who want to understand the fundamentals of how to select transfer switches. Here's a list of the learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within this session, click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. Please remember that the session will be made live at noon Central, 1 p.m. Eastern. The Q&A will start at approximately 12:45 p.m. or 1:45 p.m. Eastern, or immediately after this presentation ends if we run a little bit long. An industry expert will answer viewer questions live, and those answers will be archived with this session. And you can see the Q&A details in the Meeting tab on the left side of the screen. Here's some information about obtaining approved PDHs for today's session. Before tuning into our presentation, we'd like to share a brief video from today's sponsor.
The world is facing an ever-growing demand for power. So we're looking beyond today's challenges with the drive to invent power solutions for the new world you work in. With digital-driven engineering and thinking that have reinvented power generation to meet critical needs. With the vision to create entirely new power technologies for you, for the world, and for the future. And the imagination to rethink the concepts of sustainability and true energy independence. The people of Cummins have our eyes on your future and are the driving force behind the next generation of power.
Today's speaker is Hassan Obaid with Cummins. I'm your moderator, Amara Razgis with CFE Media and Technology. Hassan Obaid is a global technical advisor for systems and controls, critical protection at Cummins Power Generation. He focuses on technical vision, business strategy, and solving a wide range of complex problems. Hassan has been with Cummins since 2007 in a variety of roles. Power systems design engineering, project engineering, and application engineering. Hassan has designed power systems involving switchgear, controls, paralleling, transfer switches, generator sets, and digital solutions. Hassan received his bachelor's degree in computer science and master's degree in electrical engineering from Minnesota State University, Mankato. He's a regular presenter, so I do hope you'll appreciate this information. Please enjoy this tutorial, note any questions you have along the way, and then join Hassan and me for the question and answer session. You can see the Q&A details in the Meetings tab on the left side of your screen. All right, Hassan, take it away.
Well, thank you so much, Amara. I'm also very excited about this topic, but how to select transfer switches. Okay, so we have sources and we have loads and we have everything in between to make up that power system. So the typical components of your power system, the sources, which is typically a utility or that emergency backup generator. Then we have power switching components or equipment, and those are known as transfer switches, which is the topic that we're discussing today. And then you may have distribution boards in your system, And the typical name that you use for a distribution board is the commonly used name is a switchgear, and the switchgear falls under UL 1558, or a switchboard, which is UL 891. And then if we have a big system, you have what you might call a system level controller that orchestrate that entire show or that entire power system, and it acts as a single point to have access to all the data for the system. And for a world that is always on, remote monitoring capability for diagnostics, compliance reports, push notifications, and enables us to have the right technician with the right tool available to service the equipment is very much needed in the world that we live in today. So those are the components or the pieces of the puzzle of a power system. You might use some of the components that I've listed in here. And of course, there's protection, there's grounding, there's a lot of aspects to complete that entire system. But those are the major parts. We can use a few of those components to build a simpler system, such as a generator and a utility and a transfer switch. Or we can go into a very complex project that contains numerous generator sets that we're paralleling, switchgear or a switchboard, and a system level control, and entire monitoring for the entire system with complex sequences of operation, right? So those are the pieces of the puzzle. However, out of this entire system, we have to narrow down our topic today. So the focus is only on the transfer switches. Not that the other components are not important, but we just don't have time. So transfer switches are vital. Data centers, hospitals, factories, and a wide range of other commercial and institutional facilities that require continuous or near continuous uptime utilize an emergency backup generator or backup utility feed in case that main source is not available, and a transfer switch to transfer power between the two sources, right? And that transfer switch is that last link between that power source and your critical load. So those must be built, designed, and tested to a very high standard. And typically that standard is UL 1008. So again, the transfer switches are essential and the heart of every emergency power system. When you're designing a system, right, or specifying a transfer switch, there's things that we need to understand and look at. For example, we need to know, one of the things that we need to look at is the code, right? So NFPA is one of the things that I've highlighted in here. There's other codes that I'll talk about, but I don't have a slide on. But NFPA is NFPA 70, or the National Electric Code, especially Article 700, 702, and 708 require an automatic transfer switch to feed the emergency required and critical operations of a power system. 702 is optional standby. And for that, for example, there is a chance that we can use a non-automatic transfer switch. So it is important for us to understand the installation. And another code that is not listed in here is NFPA 110 Type 10. And that is, we can spend an entire presentation on discussing that, but that's where we need to have backup power available to the emergency loads in 10 seconds. But do remember that this is a system requirement, not just a transfer switch. So it involves the generator and the transfer switch. And obviously, other things we need to look at is if there's a healthcare NFPA 99, or if you need, if this will be installed in a highly seismic environment location, such as we have to look into IBC, or if this is going to California, and then maybe you have to go and look into OSHPD, which is the healthcare, and it also has a seismic element in OSHPD. So we need to kind of understand where this is applied and understand the installation type, so that we apply the right transfer switch with the right features to that application. So when you're considering or specifying a transfer switch, few things here to list that we need to look at, and those are not in any particular order, right? So we need to understand the application. Is it utility to utility, gen to gen, or the most common application, 70% of what's out there, 80% is utility to generator? Is this a service entrance or a non-service entrance? What's the switch type? Is it a transfer switch or is it a bypass isolation? What is the transition type? Is it open, closed, or is it a non-automatic where it requires an operator to initiate the transfer? The grounding scheme, and that's very important. not just for effectively detecting ground, but it's also important because that drives whether we need to go with a 3-pole transfer switch or a 4-pole transfer switch. And then there's a switch position. Typical positions are 2 position or a 3 position, and that means where are we connected? Are we connected to source 1, source 2 for a 2 position, or are we in this middle position called a neutral position, or the load shed position? I'll talk about that a little bit. Cable sizes and entry, also have to look at that. Are the cables coming from the top, from the bottom, or from the sides? And also the type of connection. Are the connections compression lugs, mechanical lugs, or is it just bus tabs with no lugs at all? So there'll be like a NEMA pattern for the holes. The enclosure, where this is installed, is it installed indoors, outdoors? Is this installed in a middle of Alaska, or is this installed in the middle of somewhere in Arizona, or is it down in Florida at a coastal region? And obviously there is the voltage and frequency, and obviously you probably start out with that in the 1-line diagram, and then there is a continuous rating for the transfer switch. And another aspect that is very essential when you're specifying a transfer switch, it's one of the most important elements, is the fault current capability. What we call is the withstand and closing rating, the WCR, and this is in the hundreds of thousands or tens of thousands, 100,000, 200,000, what have you, depending on the calculations that you do for the fault current. There is also selective coordination, and again, for that, the WCR plays along with it, and the circuit breaker that goes to protect the transfer switch, and the circuit breaker that is above the transfer switch. And again, obviously, probably one of the most important key considerations is also the codes and standards, and you probably start out with that, whether it's UL, CSA, NFPA, and IBC and OSHPD as well. So those are the key considerations that you want to look at when you're specifying a transfer switch. Transfer switch applications, utility to generator, obviously the most common application. You can have a prime power application, so you could have 2 generators, and then the transfer switch will automatically switch between the 2 sources. You can have a transfer switch that's utility to utility, and then a 3-source system. And for the 3-source system, you do need two transfer switches. So for a 3-source system, it could be I'm showing in here 2 generators backing up a utility, or it could be 1 generator backing up 2 utilities. So you'll have a utility to utility, and the second transfer switch that's below that, it's a generator. Instead of 2 generators in here. So those are the most common applications for transfer switches. All right, let's talk about the transfer switch transition type. So when we transfer, the transfer switch has 2 sources that come into it, and then the loads are connected to either source 1 or source 2. When we're switching power, when we're switching the transfer switch from either source 1 or source 2, or switching the load between the 2 sources, that transition is the transition type. And the typical the transition types that we're familiar with, or what the transfer switch can do, is 1 is an open transition, 2 hard close transition, or the third could be a non-automatic transition, right? So, but the non-automatic transition actually falls under the open transition as well. So that in itself is an open transition. So typically the transitions are open or closed. The open transition can be divided into what's called delayed transition, or it can be as fast transition sync, or also known as in phase, or fast transition no sync. So let's talk a little bit about these transition modes. So the first one is the automatic open delay transition. It is fully automatic. It's what's called break before make operation. So we're breaking the connection before we switch the load from one source into another. So the switch stops or pauses in the center position and for a predetermined amount of time. So as you can see in here, the 2 sources are available, for example, and then this is voltage versus time, and then there's this intentional time delay that we have in here. In this transfer switch, typically the transfer switch is mechanically and electrically interlocked to prevent simultaneously closing the two sources. A typical application for the open delay transition is when you're switching a load between a stored energy load, such as a large motor or an MRI machine, big capacitors. If you switch too fast between live sources, when that power is removed from the source, now the source becomes a generator. If it's a capacitor, it will have voltage at its terminals. If it's a motor, that motor will continue to spin, and then it will generate that inertia, will generate that flux. There's a flux, and then that induces voltage at the output of terminals of the motor. And then if we switched into a live source, the motor, and obviously the motor is decelerating, so that linkage between the flux and the output voltage and phase and frequency will start, and even the voltage will start to decay. And so what happened is that when we close onto another source, the source and the motor are not in sync. It will not cause damage to the transfer switch. The damage happens to the load, and it might not be immediate damage, but over time you'll keep stressing that insulation until that motor fails. Typical time delays, how long you say should I wait? Well, you can use the IEEE Orange Book and NEMA MG1. You can do the calculation. There is an Excel sheet out there that can do that for you. There's multiple methods that can be calculated, or you can use what NEMA says. They say just use 1.5 times the motor open circuit time constant. That should be listed on the motor spec sheet, or you can, if it's a big MRI machine, big capacitor, you can verify that with the vendor who are supplying that. And so the recommendation is that to wait till that open voltage decays to 22% of nominal voltage. And if we look at this curve from the IEEE Orange Book, if it's a 300 horsepower motor, we'll see that about, what is that? It's about less than 1.5 seconds. So it's about maybe 1.2 or 1.3 where it decays down to 22% of the nominal voltage. So you can say it's only 1.2 seconds, even 1.5 seconds for 300 horsepower, you're safe to transfer. And so this is why it's essential to have this 3-position transfer switch. We want to have a 3-position transfer switch for one of those options. And this is what you can use as a specification in your specs. This language in here, you can even use that verbatim. Another thing that we're going to use, the 3-position, I'll discuss it later about with respect to load shedding. Open fast transition sync, also known as in-phase transition. It's again fully automatic, break before make. We're breaking the connections before we transfer. The sources are mechanically and electrically interlocked. In this case, there is no intentional time delays. We don't put any time delays, and we want the two, because it's in phase. The transfer switch will have not a synchronizer. That's a very sophisticated piece of equipment or electrical piece of electronics. It just have a sync check. It will wait for the phase, voltage, and frequency to be in sync, and then once they're in sync, it does the transfer. Synchronizers are external to the transfer switch. Typically, you'll have those on the generator, right? So integrated generator sets now, they come with integrated smart autonomous paralleling controls, and then they'll do the synchronization between, say, the genset and the utility. Or we can use something that is not very sophisticated for synchronizing, what's called maybe set the genset to run a little faster, maybe 60.1 hertz, or we can use the slip by frequency where we wait for the two sources to be in sync, because obviously the utility might drift or the genset might drift. So again, this is called in-phase transition, typically used for resistive loads, obviously, or small inductive motors, let's say less than 20 horsepower. Some manufacturers, such as Cummins, they put in their transfer switch a fallback method. So if the synchronization does not occur we don't see the two sources synchronized within a predetermined amount of time set by you, we don't want to keep trying for the entire day till we run out of fuel, right? So it tries, and then the fallback method is to go to an open delay transition. So we'll just wait, maybe for whatever that delay transition is, and then transfer. The open fast transition, no sync, again, similar to the previous one, but we don't really care if the two sources are in sync. So they can be completely out of sync. Why? Because with no sync, the load is resistive. Irresistive loads, you really don't care for the two sources to be synchronized. The hard close transition. So we talked about open transition. Now we'll move into close transition. It's called hard close transition. The reason it's called hard is because it's less than 100 milliseconds. So we parallel both sources, source 1 and source 2, for less than 100 milliseconds. This is what the code, this is what utilities tell us to do, and then this is what UL1008 is tested for, or typically is that. But most utilities, they don't want you to parallel for more than 100 milliseconds. Sources must be synchronized phase, voltage, and frequency. And again, this is a seamless load transfer. So if you want to have a seamless load transfer, and again, obviously, you can't have a hard close transition between a live source and a dead source, right? It has, both sources have to be energized to have a close transition. When you do a close transition, though, you need to look into the intertie agreement or the utility interconnect agreement. You can't just assume, you can't just buy the transfer switch and assume the utility will be very happy of doing a close transition operation at your facility or location, right? I would encourage you to start this discussion with the utility 6 months in advance, and hopefully that will get you at the right time when you do the installation. There might be a cost depending on which utility it is, and it's not divided up just by geographical regions. Even in one state, you'll have multiple. Even in your neighborhood, you might have, well, not neighborhood, but across your city, you might have multiple utilities, and they might have different intertie agreement. So you have to look into that. A lot of times, if we have an intertie, we have a close transition operation, we might have an external relay called a parallel timer. So the timer inside the transfer switch control, it monitors the two sources and then makes sure that if once we hit 100 milliseconds, that it opens one of the sources. Some of the utilities require to have an external parallel timer independent of that transfer switch control to have that mounted inside the transfer switch, and that will also do the countdown at the same time. In case the transfer switch control fails, we have a backup. You might also have a reverse power relay, because we don't want to, if we see a certain amount of kW going back to the utility for some amount of time, is we want to do something. And then there's a lockout, the 86 lockout, and this is, we can use that to either indicate some alarms or shunt trip transfer the utility breaker in case we're parallel for more than 100 milliseconds. So again, for hard close transition, please pay attention to the code, to the utility and the intertie agreement. Okay, so we've covered the open close. Let's talk about this non-automatic transition. It's a fully break before make operation. It is very similar to delay transition. It requires an operator to go and initiate the transfer. But the difference in this non-automatic is that it is all the time delays, the controls, the smartness, all that is still exists in there. So it requires an operator to, for example, to place a transfer switch in a position, or another key to transfer between, or push button, but typically keys is to transfer between source 1 and source 2. Again, this is non-automatic. So if the utility fails, even though the genset starts, the transfer switch is not going to transfer between between the sources. It will wait for an operator to come and initiate that transfer. I say that non-automatic in the last note is not the same as a manual transfer switch, because non-automatic transfer switches nowadays are become very smart. They have the controls, they have the smarts, they have the protection, they have the metering capability. So it's almost like an automatic transfer switch, because the manual transfer switch is typically, again, it requires an operator to transfer between the two sources, but it has a very rudimentary control, very simple control. It could be even lights with, which again requires an operator to initiate the transfer. Do note that if we go back to slide number, I don't know, 6 or 7 or 8, where I listed the NFPA, the National Electric Code, NFP 70, that NEC requires automatic for life safety and legally required, and COPS operation, you do require to have an automatic transfer switch. You can't use a manual or non-automatic. So we're talking a little bit about the controls. Let's talk about the time delays. Transfer switches, the controls and transfer switches typically have multiple time delays. Those are the time delays that you want to specify in your specs, or you typically would expect a transfer switch to have. So there is the engine delay time, and the numbers between parentheses is the typical range that you see in the controls. The time delay engine start, so that we avoid nuisance starting. Engine cool down. This is obviously want the engine to cool down safely. And this varies, typically 10 minutes, but it depends whether you're in Alaska in the middle of winter or whether you are in a very hot region in, let's say, I don't know, in down south in Texas. Normal to emergency, retransfer time delay, pre-transferring back to the utility, the program transition delay, which we just discussed. And then there's an elevator signal, whether it's pre-signal or a post-signal, that allows the elevator to go down to a floor and then open up the door. So basically all this does is the transfer switch signals the main elevator PLC and tell it what's going on between the two, or the other way around. Transfer switch controls, typically they are microprocessor based, with a lot of information readily available from the transfer switch. So you can see date and time, whether the transfer switch is protected with a password or not, contextual icons, banners that tell you what the countdown for a timer, so what's happening to keep the operator in touch with what's happening in the system. Voltage, which source is available, which source we're connected to. And all these obviously will change, and alerts will pop up depending on what's happening in the system. And also we typically expect to have a real-time clock inside the transfer switch as well. You may want to have, also different level of protections, password protection in the control, so we don't have anybody messing around with the settings, and you might have multiple levels, one level that has all the power, another level in between as, say, an operator, and then there's a user that we just want to give them to see the information and not mess around with any settings. Voltage sensing and protection. We expect that this to be a true RMS voltage sensing from the control itself, and we want to have sensing on both sources, source 1 and source 2, and on all phases, phase A, B, and C, because obviously you can easily lose one phase from the utility, but we also want to have that, have to have a redundancy and complete protection for our loads. And so we want to have also sensing on the 3 phases, on the generator, or on the other source as well. I expect that we monitor and compare the phase rotation of each source, and then maybe there's some current detection for it would exceed a neutral current when it exceeds a certain threshold. Sync checks, again, we want sync check. Typical sync checks are phase and frequency, because those are the most two that will be out of phase or out of sync. If you're transferring between a generator and a utility, you'd expect the utility to always, if it's a 480, you expect that to be plus minus 2%, right? But if it's not, and then the genset will always, because it's tight loop, it has this PID tight loop, so that if we set it at 480, it will very likely be at 480 or 481 or maybe 482. The reason we want to have a voltage, also sync check for the voltage, is because if the voltages of the utility is off by 5 or 6% from the generator, the one with the higher voltage is going to push current, and if you push current around, a circuit breaker is going to trip, and then we're going to be in the dark. And obviously we expect that the built into the control itself detection of loss of phase on all 3 phases or a single phase. And now we can have metering capability built into load metering capability built into the control itself, or quality metering. We can get not only the phase rotation and the voltage and frequency and real and reactive power and apparent power, but we can also get total harmonic distortion to maybe if there's a problem with our loads that we need to investigate and solve. Event data tells us what's happening, what's any alerts, any active alerts, if this product, the transfer switch is not an auto, and warning and information. We get a fault code that with a code description, and then that way we keep in touch if there's a problem in the system, that we bring in the right technicians with the right tools, or if there's something that we need to troubleshoot. History of events, we expect to see also the fault codes, the active time delays, and the tests and exercises, and some user-driven inputs to also be available to us, and keep a record of all that so that we can go back and look what happens in the last 100 events or 200 events. Okay, now that we talked about the control and the transition nodes, let's talk a little bit about the switch mechanism. So typically we see in the spec that the switch action is double throw, mechanically held in both directions. So it's double throw. That means this is in here linked in a way so that you can never close the two sources together, right? The transfer switches can be in source 1 or source 2, or can be in this middle position, the neutral position that I discussed earlier, right? The load shed position, or the program transition that puts the transfer switch in the center position and wait for that time delay. So now the advantage of this neutral position, don't confuse that with a neutral pole, by the way, is that if there is an overload on the generator, we want to shed that transfer switch. If we shed the transfer switch, we don't want the load to be connected to a de-energized source. If we connect that to a de-energized utility, if the utility comes back, first of all, you don't know when it will come back, and if it comes back, you don't know if the voltage or the phase, well, if the voltage is at the right level. So you can cause damage to your load, right? So this is why you want to specify a 3-position transfer switch to be in the safe, so if there's an overload, we can shed, and so we don't cause damage to the load. Now, you may be required to have load shed per code, because the emergency backup generator can be used to feed your emergency, legal required, and optional loads if you have enough capacity, or if you are required to have selective means to shed the non-critical loads. So this is known as, this is a 3-position transfer switch, because we have, the load can be connected to source 1 or source 2, or it can be in this neutral position, the center off position. Don't confuse that with neutral switching. Neutral switching is, we have 3 poles, A, B, and C, and the neutral. And we say that this is simultaneously switched. This is my best attempt to draw a picture for you and convey the message. So if it's not clear, I apologize about that. There's a common crossbar that switches all the 3 sources and the neutral. If this was this is a 4-pole transfer switch. If this is a 3-pole transfer switch, so this would stop right here, and this would be solid connection, or just one continuous connection. We say that the neutral should be simultaneously switched. We don't want an overlapping neutral. An overlapping neutral has a separate mechanism that is not rated as the same three poles or the 3 phases. And again, this adds complexity, another piece that can fail. And then what if it fails and it feels closed? Because again, with the overlapping, momentarily the 2 neutrals between one source and the other are paralleled. So that is can cause problem for your grounding schemes. So we want to specify simultaneously switched neutral that switches all the 3 phases. And again, this is the same rating as the 3 phases in terms of capability and capacity. Well, with the 3-pole, so this is a 4-pole transfer switch. So this takes us to the 3-pole versus 4-pole. We can spend an entire day just discussing this one slide, but we're going to spend it in 1 minute in here. So when do you need a 3-pole and when do you need a 4-pole? Ground fault sensing depends on being able to sense ground current, right? Ground fault current. We need to accurately sense the ground fault. And so if we need to do that, we must have a path that we know, or a known path for the electrons to return back to the source. If there's no known path, or if that path is not identified, those electrons will find their way back to the source. And either through the operator, and hopefully not, or through other means, right? So again, we can spend the entire day discussing this, but I'll give you the summary. In order for us to have an effective ground fault sensing and detection, there are two rules. That's it. This is the only thing we're going to get. There's those two rules. There shall only be one neutral to ground connection at one time. So one neutral to ground bond at one time. And the ground fault sensor, which is the CT, right? This is CT in here and CT in here, must be downstream from that bond as you look into the source. So if you put your eyes in here and you look this way, this is the utility. If you put your eyes in here, you look this way, this is the generator. And this is the bond, and this is the CT. So to have it effectively is that if we look this way, because you can be connected either to this source or to this source. If we're looking this way, the sensor is downstream from the bond. If we look this way, the sensor is downstream from the bond. And in order for us to satisfy those two rules, we need to have a 4-pole transfer switch. So the 4-pole transfer switch satisfies those two rules, and this is when you would need a 4-pole. So if you need to have if there's a need to have a ground fault protection, and you need to have this to be effective ground fault protection, you need to specify a 4-pole transfer switch. It might not be very clear, but if we walk through this scenario slide by slide, you will see why that's needed. But here's just a summary of that. So discuss a little bit about separately derived versus non-separately derived. You can read the NEC book. I'll give you just a quick summary in one slide. This is a separately derived system with some of the requirements in here. Basically, separately derived system is that when we switch it requires a 4-pole transfer switch. If we're switching between the two sources, we must break the 3 phases and the neutral. That's it. In a non-separately derived system, the neutral is solid or connected from one source into another. So you just need a 3-pole transfer switch. That's the separately derived versus non-separately derived. Okay, I hope you're still with me with this presentation. I'm going to switch gears in here and talk about understanding and applying transfer switch short circuit ratings. I know there's a lot of information to grasp on here today, but hopefully this will be all good information. So what you'll see on the label is you'll see the short circuit withstanding closing ratings, and you might also have what's called the short time rating. And the manufacturers list this information to the maximum level. So the maximum voltage, the maximum durations, and the maximum RMS short circuit. What that means is that you might ask, well, if I listed at 600, what is the value at 480? Well, you typically would just think, the laws of, physics will say that it will be more, but unless it's printed on the label, the number that you're going to carry is 150,000. So it's 150,000 at 600 and 480 and 208 for up to 0.05 seconds. If it's more, again, this is at the maximum. So let's go ahead and describe this. Where does this information come from? So the leading standard for testing transfer switches is UL 1008. It's the standard for safety for transfer switch equipment. They specify very stringent test requirements. And by the way, UL 1008 is harmonized with the CSA 22.2 178.1. They're very similar, very minor differences. They specify a temperature rise test, dielectric voltage withstand test, an overload test, endurance test. And then you are required to have a short circuit test. And then they do a dielectric voltage after that. And then they specify also, they don't specify, but they in the standard they have an optional test which is called the short time current test. So we'll talk about that here shortly. Clearing a fault versus withstanding a fault. Look, over current protection devices, OCPDs are designed to clear a fault, and by clearing a fault is opening up the circuit breaker. If there is a fault, a fuse or a circuit breaker are intended to break that circuit and break that electromagnetic force, overcome all the forces and open up the circuit, right? So we don't cause damage. So they have what's called ampere interrupting capacity, AIC rating. And the AIC is the maximum available fault current that an overcurrent protection device can safely clear a fault when a fault is applied at its load site. Transfer switches, on the other hand, are not rated to clear a fault. They are rated to withstand a fault. What that means, if there is a fault that is going through the transfer switch, and let's say it's this obscene amount of current, I don't know, 125,000 amps of current going through the transfer switch, we don't want the contacts on the transfer switch to even move by 1 micron. We don't want them to shift. If they open up by a little bit, that's when we have catastrophe, right? So the transfer switch contacts must stay closed if there is a fault, unlike a circuit breaker that is intended to open. So transfer switches must be protected by an overcurrent protection device on its terminals, and transfer switches have what's called the WCR rating. What's the WCR comes from? Well, let's just say that we have a source 1 is available, the load is downstream. If there is a fault, the transfer switch must withstand that fault. But if there is a fault, what happens is that this OCPD opens. If this OCPD opens, and let's say this is a utility that's already available, or maybe it's a generator and this fault hasn't been cleared, so the transfer switch might signal the genset to start. So then the transfer switch must be, even though the fault still exists, and then we must be able to close on the fault. And so transfer switches get this rating called withstand closing rating, WCR. The withstand starts with the contacts closed, and then a specified amount of current is applied for either a specific duration, say a quarter of a second, or a half a second. Let's just use cycles, 2 cycles, 3 cycles, or 5 cycles, or 6 cycles. But again, UL 1008, by the way, they don't recognize cycles, they just recognize time. So I'll show you the times here coming up shortly. Or until a specified OCPD trips a specific overcurrent protection device. The closing test starts with the contacts open, then we close onto the fault. The same transfer switch must close onto the fault current under the same conditions. The same set of contacts are used for both tests, withstand and closing. When you specify a transfer switch, you want to make sure that it's withstand and closing rating. Withstand without closing is not a true rating for a transfer switch. The UL 1008 short circuit test requirements, it lists the available currents, times, and a power factor and a time duration. A manufacturer can deviate and go to a worse numbers, but not better than these numbers. So you can go to a worse power factor for a longer duration, for higher currents. They also, again, these are the acceptable time delays at time testings. The most common durations that you're familiar with is the 0.05 seconds, which is at 60 hertz is 3 cycles. And then they list available fault current. If we go and list a number that is not one of those numbers, it is not recognized by UL. So I can't put on a transfer switch a number of 75,000 amps, 75.23 thousand amps, right? It has to be one of those values. The short circuit passing criteria for transfer switch is the ability to operate the switch, no breakage, doors must stay secure, the contacts must not be welded, and pass a dielectric test. And so what that means is that after a fault, if something happens and the transfer switch doesn't transfer, an operator can come open the transfer switch and manually switch over if they need to. But again, it's safety. No one gets hurt, nothing gets blown up, and we can still transfer to another source if we need to. How do we apply the transfer switch rating? So basically, you do the calculations using ETAP or SKM, and let's say you might have one board, or you might have multiple boards, and that fault current keeps going down. Basically, you want to have an OCPD protecting the transfer switch. Select a transfer switch. So the available fault current is 150,000 amps. The WCR in here must be, at this terminals, must be able to handle that. You don't want 100, if it's 150,000 amps, but now as you go down in the distribution boards, the fault current goes down to the resistance. Now it's 65,000 amps. You really don't need 150,000 amp WCR down here. It's not needed because you went down in the distribution board. To protect the transfer switch, you can apply the time-based, which we can use a generic transfer breaker, or we can use a specific breaker tested with a transfer switch that is the manufacturers puts on their specification, on their labels for the transfer switch. However, some of the challenges with what I just discussed earlier is that the detailed coordination studies usually are not been completed. The transformer has not been identified, so we don't know what the resistance is or the impedance is. Typically, you can specify it at 6.7% or so. Unknown distribution board, which I know this is from a consultant engineer, is the most common problem, is that we don't know the switchboard, the switchgear, we don't know the breakers that go with it. Limited space electrical room, so we might have to transfer switch, upsize it to meet the short circuit requirements. And then the changes to the breaker, new breakers coming up from the manufacturers of circuit breakers, and then there has been some changes to UL 1008 7th edition. So that new testing has to be done for the transfer switch to be tested with a specific breaker. So this, with those two, with whatever I listed on these, some of the challenges that you have as a consultant specifying engineer, what we can do is we can apply the time duration rating. Again, it's a short circuit withstanding closing rating. If we go back to the previous example, it lists at 150,000 amps, the maximum voltage and the duration. If you remember, if we go down in the distribution board, one more board, it was at 85,000 amp. We look at this transfer switch, it has this following label that it's rated for 85,000 amps at 600 volt max for up to 0.05 seconds. You might say, what is the value at, say, 1.25, right? 0.0125, which is, again, is going to be, obviously, if I can handle 85,000 amps at 600 volts for up to 50 milliseconds, I can handle that amount of time for less than a 50 millisecond, right? For half of that, it's obvious. So what that takes me to is that if I use the time duration rating, right? So you can use the protected transfer switch, you can use either the time-based or the specific breaker. Both protect the transfer switch, but it depends on your application, how you want to apply it. The time duration, if we have a high WCR transfer switch that's listed for a very high time duration, this gives you the flexibility to select, or the freedom to select, a generic UL489 breaker, so you don't have to worry about, does this breaker coordinate with this transfer switch? That solves all those problems that you've been dealing with for years. So what you want to get out of this is that a high time-based short circuit WCR, withstanding closing ratings, simplifies the breaker selection. You might ask, well, I've heard this rating called the any breaker rating. What is the any breaker rating? The any breaker rating is just another way for stating the time duration rating. It's not a true rating, it's just a time duration. It comes from the requirement for 489 circuit breakers that a breakers above 400 amps will trip in 0.05 seconds. Less than 400 amps, they'll trip in 0.025 seconds. But the any breaker rating is not a rating, it's just another way for stating the time duration. What you want to put on your specification, you just want to list what is the available fault current, what is the voltage. That's what you want to specify, right? And that will allow the manufacturers to give you the transfer switch with the right ratings. There is the last thing I want to discuss is the short time test, right? The short time current test that is not required by UL, but a manufacturer of a transfer switch can go above and beyond and say that, you know what, I want to prove that the transfer switch not only can handle the fault current, but it can still be used again if we need to in the circuit, because we must pass all the testing criteria for the WCR plus pass a temp price test. So the short time rating, it can be used if you have a UL 1558 switch gear that is designed to handle current for up to 30 cycles or a half a second. So we can coordinate that with that UL 1066 breaker. And so you'll see in here, both are a short circuit or a short time, both are short circuit capability of the transfer switch, and both must be withstand and closing rating. Even the short time must be withstand and closing rating. As you can see that the same transfer switch can handle 125,000 amps of fault current for a maximum of a half a second, or the same transfer switch, if you put a circuit breaker ahead of it, and that breaker trips in 0.05 seconds or 50 millisecond, it can handle up to 150,000 amps. It all related to I squared T, more current, shorter time, more energy in less time. So how do we coordinate this breaker, and what's the advantage of it? Is that, you know, if you have a 1066 LSIG breaker, you have about 6 or more knobs that you can change. With a 1066, we can turn off the instantaneous, right? Because it's in that switch gear. But remember, everything must be braced to handle. So the cables between it and the next board or the transfer switch must also be able to handle that fault current for that duration. And so now that will help us with the transfer switch if it has that short time rating to coordinate with that breaker. When do we need that for? Is if we do selective coordination, right? So you're required to have, you know, NEC 732, 701.32, and 708 that devices shall be coordinated, right? The system is not coordinated. Everything, if there's a fault, everything is trips, versus in here, this is selectively coordinated. This fault current, if there's a fault downstream, we trip the circuit breaker closer to the fault. But what that means is that the transfer switches, the breaker strip, the transfer switches that are in between these boards must be able to, or braced for that short circuit in that specific branch for that duration. So this is the important thing that you want to get out of the slide. So which takes me to this, and then only got one more slide left, and then we'll turn it over to questions. Using the short time ratings, you obviously don't want to use a short time rating in all the distribution boards all the way down, but looks like this moved a little bit here, but just use your imagination that this is connected to the board. Is that with the high short time rating, the transfer switch can handle the short circuit for a longer time and can still be used in the circuit, just like a 1066 breaker. You know, it sees ungodly amount of current, and that it still doesn't blow from its place, and then allows us to have the breaker downstream isolate that fault. So if we go back to the challenges that you have, the high short time WCR helps you also in selective coordination strategies. And this takes me to the last slide, which is how to select transfer switch and the summary. I hope you enjoyed the course and I hope you learned something. I know it was a lot of information to pack, but transfer switches provides means for transferring loads between power sources. 4-pole transfer switches should be used when you need to have ground fault sensing, when if it's ground fault protection is required. Transfer switches have short circuit withstanding closing rating and short time ratings. The time-based rating, a high time-based rating, simplifies the breaker selection, and also if you want to have coordination for, let's say, up to a half a second, the short time rating is with a very high short time withstand and closing rating will enable the selective strategies for you to have selective coordination strategies. And thank you so much. And now I'll turn it over to Amara.
Yeah, thanks, Hassan. That was a ton of fantastic information. And now it's time for the question and answer portion. Please submit your questions using the Zoom question and answer interface. Today's speaker is Hassan Obaid with Cummins Power Generation, and I'm Amara Razgis with CFE Media and Technology.